Alright, so as you may have guessed by watching these videos, these aren't necessarily made in a linear fashion, meaning that I'll make a video and then maybe a month later I come back and I make a video supplementing it. And this particularly becomes true when I had to make videos for a test and then I go back and say, oh, there's gaps missing. So the microreaction we're about to talk about here, clearly this video is a newer video based on the other video I have on this. And it came about because as much as I love Carrie, and that book really deserves a lot of praise, it is a good book, you can definitely tell towards the back end of the book that Carrie was kind of outside, the topics were outside of the scope of the book. And particularly with the microreaction, this was true. So your book Carrie kind of gives like this one paragraph explanation of the microreaction, and it's this really complicated cyclic reaction. Well, actually the microreaction is a lot more than what the book talks about. It's a very synthetically useful reaction. And it's also not limited to the cases that you see in the book. So the microreaction itself, more broadly speaking, is the reaction of some carbene reacting with an unconjugated compound. Now, this R group here typically is going to refer to a ketone or an aldehyde. So it's usually an alpha-beta unsaturated alkene. But really the R group only has to be a very strongly electron withdrawing group, because what we're trying to do is we're trying to reduce the electron density on this to make it an attractive nucleus, or make this attractive to a nucleophile like a carbene. Now, again, your book covers these carbenes by using diketones and removing a hydrogen from it, but this can actually be any carbene. So, example your book gives is deprotonating compound like this with a strong base, or we can work with something like a Grignard or organolithium. The only point here is that we need a carbene. So what happens? Well, our strongly electron withdrawing group will drive a nucleophilic attack by the carbene. And typically what's going to happen is that if we consider the R group, we have an alpha and a beta. The attack is going to be on the beta carbon. So we get an attack which subsequently results in, put a prime here, a carbene being formed on this longer chain compound. Now, why we typically want this R group on the what's going to be attacked by the microreagent, the carbene, to be a ketone is that this is going to stabilize those lone pairs by resonance. So if this R group here is a ketone, we can get resonance stabilization. This is followed by an acid workup. And this acid workup here is going to either provide a hydrogen to the carbon or, depending on what this group is, protonate that. But this is the bigger picture of the microreaction. We have a carbene, our microreagent, reacting with typically an alpha-beta unsaturated ketone, but this R group can pretty much be anything, particularly if that anything provides some form of resonance stabilization to the resulting carbene that's formed on this chain. So if we have something like a nitro group, we can definitely get participation. So this is the bigger picture of the microreaction. Carbene plus an unsaturated alkene reacting to form carbon-carbon coupling, which we follow with an acid workup to give us the final product.